Three-phase induction motors are the most widely used electric motors in industry. They run at essentially constant speed from no load to full load. However, the speed is frequency dependent, and consequently these motors are not easily adapted to speed control. We usually prefer DC motors when large speed variations are required. Nevertheless, the three-phase induction motors are simple, rugged, low-priced, and easy to maintain, and can be manufactured with characteristics to suit most industrial requirements. In this chapter, we shall focus our attention on the general principles of three-phase induction motors. Like any electric motor, a three-phase induction motor has a stator and a rotor. The rotor carries a three-phase winding called the stator winding, while the rotor carries a short-circuited winding called a rotor winding. Only the stator winding is fed with a three-phase supply. The rotor winding derives its voltage and power from the externally energized stator winding through electromagnetic induction, and hence the name. The induction motor may be considered to be a transformer with a rotating secondary, and can therefore be described as a transformer type AC machine in which electrical energy is converted into mechanical energy. The advantages of this motor are: it is simple and rugged in construction. It is relatively inexpensive. It requires little maintenance. It has high efficiency and reasonably good power factor. It has self-starting torques. And a couple of disadvantages is the facts that it is a constant speed motor, and its starting torque is inferior to a DC shunt motor. However, it does have a starting torque. A three-phase induction motor has two main parts, a stator and a rotor. The rotor is separated from the stator by a small air gap, which ranges from about 0.4 millimeters to 4 millimeters, depending on the power of the motor. The stator consists of a steel frame, which encloses a hollow cylindrical core made up of thin laminations of steel, silicon steel, to reduce the hysteresis and eddy current losses. A number of evenly spaced slots provide the inner periphery of the laminations where the coils are wound. The insulated windings are connected to form a balanced three-phase star or delta connected circuit. The three-phase stator winding is wound for a definite number of poles as per the requirement of speed. The greater the number of poles, the lesser the speed of the motor, and vice versa. When three-phase supplies are given to the stator winding, a rotating magnetic field of constant magnitude is produced. This rotating field induces currents in the rotor by electromagnetic induction, the same way that it was done with the two-phase induction motor. In this example, a three-phase machine stator has 3 sets of coils, mechanically spaced 120 degrees apart. Each coil is split in half, creating 2 poles, essentially a north and south pole, which I have designated X-X primed, Y-Y primed, and Z-Z primed, and when energized will produce a magnetic field pointing in the direction of the unprimed half of the coil. When these three windings are energized from a three-phase supply, a rotating magnetic field is produced. This field is such that it does not remain fixed in position, but rotates smoothly around the stator. The direction of rotation of this field will depend on the sequencing of the three-phase supply. For this reason, it is called a rotating field. It can be shown that the magnetic or the magnitude of this rotating field is constant and is equal to 1.5 phi m, where phi m is the maximum flux due to any one of the three phases. To understand the concept of the rotating magnetic field in our two-pole three-phase stator, we will apply a set of currents to the stator, naming the three phases X, Y, and Z. They are energized from a three-phase source, and currents in these phases are indicated as I subscript X, which is Im sine omega t, I subscript Y, which is I subscript m sine omega t minus 120 degrees, and I subscript Z, which is equal to I subscript m sine omega t minus 240 degrees. These three currents are all of the same magnitude, and they are all of the same frequency. They are just separated by 120 degrees. The fluxes produced by these currents are, of course, in phase with the currents, and shown in the time domain here are given by phi x is equal to phi m, or phi maximum, times sine omega t. Phi y is equal to phi m sine omega t minus 120 degrees, delayed from IA by 120 degrees. And phi z, which is equal to phi m sine omega t minus 240 degrees, which means it is delayed from IA by 240 degrees. Here, phi m is the maximum flux due to any phase. This shows the phasor diagram of the three fluxes. We shall now prove that this three-phase supply creates a rotating magnetic field which rotates smoothly around the stator. Let's take a snapshot of the phasors, call it instant 1 or instant number 1, and that's going to take place at t is equal to 0, or the time is equal to 0. Since omega t then equals 0, the flux in phase x, the red phase, is 0. Phi x is equal to 0. We can find the flux in the other two phases at the instant in time by plugging in 0 for omega t in their formulas. For example, giving us the magnitude of the blue phase, phi m, times sine minus 240, which works out to be root 3 all over 2 phi m. Doing the same thing for the y phasor, or the green phase, it works out to minus root 3 all over 2 phi m. So these are the magnitudes of the fluxes at time 0. Now remember, these coils are mechanically separated by 120 degrees. So the blue, or the Z phase, is going to be pointed in this direction, And we calculated the magnitude to be the root 3 all over 2 phi m. And the green phase or Y phase flux, if it were positive, would be in this direction because of the coil positioning in the stator. But at t equals 0, we know the magnitude of this is minus root 3 all over 2 phi m. We now have two flux phasors that will be acting on the rotor. In order to find the resultant flux, we simply add the two phasors together. So graphically, doing that, we move the green phasor to the head of the blue phasor, and the resultant will be found by joining the tail of the blue to the head of the green. And we know that the coils are separated by 120 degrees and that the magnitude of the green phasor and blue phasor are equal. So that means the angle between the resultant and the blue phase must be 30 degrees. We can now use our trigonometric functions to calculate the magnitude and direction of the resultant, or the black arrow, which is 2 times root 3 all over 2 phi m times the cosine of 30. The cosine of 30 is just root 3 all over 2, so our answer is 2 times the root of 3 all over 2 times phi m times root 3 all over 2, which gives us 1.5 phi m for the magnitude, and it is pointing straight up, which is 90 degrees. We now will move to an instant number 2, which is at 30 degrees, meaning that omega t is equal to 30 degrees. At that point, the magnitude of the red phase is phi m all over 2. The magnitude of the green phase is phi m. And the magnitude of the blue phase is also phi m all over 2. In the vicinity of the rotor, the red flux phasor is plus phi m all over 2. The blue flux phasor is also phi m all over 2. And the green flux phasor is phi m, but it is minus, so it will be in the reverse direction. It will be at an angle of 60 degrees with the red flux phasor. We're going to add the three phasors together. So we put the tail of one on the head of the other in a series, and the resultant will be, and I will label it phi subscript r for the resultant phasor. And it will be the vector sum of all three phasors. Phi m all over 2 minus phi m plus phi m all over 2. I'm going to move the last two vectors around just for the ease in doing the analysis. These two phasors, the red and the blue, added together will give us phi m all over 2 at 60 degrees. We know that the magnitudes of the red and the blue phasors are identical, and they are at 60 degrees, so they form an equilateral triangle. That means adding the red and blue phasors together will give us a resultant phasor, phi m all over 2 at 60 degrees. Adding the green phasor, which is phi m at 60 degrees, which adds to our previous phasor calculation to give us the resulting flux of 1.5 phi m at 60 degrees, which exactly matches up with our previously calculated phasor at 90 degrees but shifted 30 degrees. Note that the magnitude, 1.5 phi m, has remained constant. I'm going to leave our resultant flux phasor on the diagram for reference purposes. And moving to the instant number 3, which is 60 degrees, meaning that omega t is 60 degrees. And we're going to go through the same process here. The only thing is our angle, omega t, is going to be 60 degrees. Since the blue flux phasor is 0 degrees at this point, we will leave it out of the calculation. The red flux phasor is at 60 degrees, and it is root 3 all over 2 phi m. The green flux phase at 60 degrees is minus root 3 all over 2 phi m. The resultant flux phi r is going to be the sum of just these two phasors because, as I said, the blue phasor is equal to 0. The red phasor we will plot in the vicinity of the rotor is plus root 3 all over 2 phi m. The green flux phasor is minus root 3 all over 2 phi m, which, if it was plus, would be in this direction. But again, it is minus, so it is going to be in the other direction. We're going to add those two phasors together, which gives us a resultant, which is 30 degrees ahead of the red flux phasor. Doing the analysis of a 30, 60, 90 triangle, what we come up with in regards to the magnitude when adding those two phasors together is to root 3 all over 2 phi m times cosine 30 at 30 degrees. And we know the cosine of 30 degrees is root 3 all over 2. So our equation now looks like this, which gives us the resultant flux phasor phi r equal to 1.5 phi m at 30 degrees. As you can see, it is the same magnitude as our previous results, but again, it is shifted another 30 degrees. The next instant in time that we're going to look at is instant number 4, which is at 90 degrees. Again, meaning that omega t is equal to 90 degrees. Again, I am leaving the previous calculated resultant phasor, the black arrow, so that we can compare what we find this time. At this instant, the red phase flux is phi m, and the green phase flux is minus phi m all over 2, and the blue phase flux is also minus phi m all over 2. As before, the resultant flux phase flux phi r is the sum of the three flux vectors or phasors. The magnetic flux phasor in the vicinity of the rotor are the phase flux plus phi m. When plotted, the green flux minus phi m all over 2. If it were positive, it would be in this direction, but it's negative, so we're going to put it in this direction. When we plot the blue phase flux minus phi m all over 2, if we were to plot it positive, it would be in this direction, but again, it's negative, so it's going to be in this direction. If I'm going a little bit fast here, it's because the process is the same, and we're just going to speed through it. Some of the numbers are different, of course. Adding all three flux phasors in the vicinity of the rotor graphically, and adding these phasors, I will rewrite them in polar notation. The red phi m is phi m at 0 degrees, and minus phi m over 2 green and minus phi m all over 2 blue results in a polar notation of plus phi m all over 2 at 0 degrees. I know this from some of the results before, and it's just the third side of an equilateral triangle. All added together results in a phasor, which is I've indicated as a black arrow, for instant of time number 4. Written in polar notation, it's 1.5 phi m at 0 degrees, which, as you can see, is the same as the last calculated phasor, shifted 30 degrees. So you get the idea of what is happening here. We have picked 4 instants of time, and we found that the resultant flux phasor has rotated from 90 degrees to 0 degrees, and because we did it in steps, it looks like it's 4 steps to the process. But indeed, the one constant of this is the fact that the magnitude of the phasor is constant, 1.5 phi m. And you have to take my word for it, or actually we'll prove that in a little while, but the phasor shifts smoothly in a clockwise rotation. And if we went through all the various degrees, you would find that the phasor would be still constant at 1.5 phi m for its magnitude, and it would continue to rotate in a clockwise manner. We shall now use another useful method to find the magnitude and speed of the resultant flux due to three-phase currents. The three-phase sinusoidal currents produce fluxes phi x, phi y, and phi z, which vary sinusoidally like this for the red phase, or the X phase, like this for the green phase, and like this for the blue phase. As you can see, the fluxes are represented by 3 variable magnitude vectors. The individual flux directions are fixed by the physical positions of the coil, which are separated by 120 degrees. But their magnitudes vary sinusoidally, as does the currents that produce them. These are what we call pulsating fluxes. And they produce a rotating field of constant magnitude equal to 1.5 m. The resultant flux at any instant will be the vector sum of all three at that instant given by x, y, and z flux vectors. To find the magnitude of the resultant flux, I will resolve each flux x, y, and z into horizontal and vertical components, then find their vector sum of those two components. So the resultant of the sum of phi x, phi y, and phi z, or phi r, can be written as the sum of phi m sine omega t for the red flux phasor plus phi m sine omega t minus 120 degrees for the green, and phi m sine omega t minus 240 degrees for the blue. As I have already stated, I'm going to rewrite this in terms of their horizontal and vertical components. Since the flux direction is set at either 0, 120, or 240 degrees, we can find their horizontal components by multiplying by the cosine of the individual angles. Finding the sine and cosine of 120 degrees can be accomplished by considering the ratios of the sides of a 30, 60, 90 triangle. Sine 120 degrees equals plus root 3 all over 2, and cos 120 degrees is minus 1/2. And similarly, finding the sine and cosine of 240 degrees can be accomplished by again considering the ratios of the sides of a 30, 60, 90 triangle. Sine 240 degrees is going to be equal to minus root 3 over 2, and cos of 240 degrees is minus 1/2. Rewriting the equation using these ratios gives us this long equation. Next, I want to get rid of the difference of angles, which I do using the trig identity. Sine alpha minus Bravo angles is equal to sine alpha cos Bravo minus cos alpha sine Bravo. And I can substitute for alpha and Bravo with looking at my green trig identity sums. Sine omega t minus 120 degrees can be rewritten as sine omega t cos 120 degrees minus cos omega t sine 120 degrees, which can be rewritten sine omega t times minus 1/2 minus cos omega t plus the root 3 all over 2, which again can be rewritten as minus 1/2 sine omega t minus root 3 all over 2 cos omega t. Looking at our blue sum, it is actually going to be sine omega t minus 240 degrees, which is equal to sine omega t cos 240 degrees minus cos omega t times sine 240 degrees. That can be rewritten with the substitute of the cosine and sine of 240 to give us sine omega t minus 1/2 minus cos omega t minus root 3 all over 2. And rewriting it again, it could be equal to root 3 over 2 cos omega t minus 1/2 sine omega t. I can now substitute these values for sine omega t minus 120 and sine omega t minus 240 and come up with this long equation. Now I'm going to bring the minus 1/2 inside the brackets, which will change the equation to look like this. And removing the brackets, the equation now looks like this. Plus phi m root 3 over 4 cos omega t negates the minus phi m root 3 all over 4 cos omega t. Leaving us with phi m sine omega t plus phi m 1/4 sine omega t plus phi m 1/4 sine omega t, which equals 3 over 2 phi m sine omega t, which is equal to 1.5 phi m sine omega t. Now, in terms of the vertical components, remember that the flux direction is set at either 0, 120, or 240 degrees, which means we can find their vertical components by multiplying by the sine of their individual angles. Finding the sine of 120 and 240 degrees can also be accomplished by considering the ratio of the sides of a 30, 60, 90 degree triangle. So sine of 0, of course, is 0. The sine of 120 is plus the square root of 3 over 2. And the sine of 240 degrees is minus the square root of 3 all over 2. Next, I want to get rid of the difference of angles, which I do in the same manner that we did in the previous slide, using the trig identity. Sine alpha minus bravo is equal to sine alpha cos bravo minus cos alpha times sine bravo. And we can again replace those difference values with the trig identity values. Bringing the plus root 3 over 2 and minus root 3 over 2 inside the brackets. Then we'll remove the brackets. The equation now looks like this. Plus phi m root 3 over 4 cos omega t negates with minus phi m root 3 all over 4 cos omega t, and plus phi m 3/4 cos omega t negates minus phi m 3 over 4 cos omega t, which means all of our calculations that we've gone through basically tells us that the vertical component of our resultant vector is 0. Now, you might think, well, we went through a lot of calculations just to end up with 0. But I wanted to bring it forward mathematically so when we get to the end you can see how it works out. So we have calculated the horizontal and vertical components for the resultant flux. The resultant flux magnitude is given by phi r is equal to the square root of the horizontal component squared plus the vertical component squared, which is equal to the square root of 1.5 phi m sine omega t all squared plus 0 squared, which of course is 0. And if we find the square root of that, it is the resultant flux vector is equal to 1.5 phi m sine omega t, which is a phasor of constant magnitude 1.5 phi m rotating at an angular velocity omega. Now that angular velocity can be in cycles per second or radians per second, as long as you're consistent. Here we see the stator generated fields phi z blue, phi y green, and phi x red. The flux field I have represented by colored vector arrows. Notice that the flux fields are stationary, held in place by their respective stator coils. However, they do oscillate 0 to positive, 0 to negative, all oscillating at system frequency omega. The green and blue crossings are delayed by 120 and 240 degrees respectively. When you add these vector arrows, they result in a generated field phi r, which I've indicated in black, that is of constant magnitude and changes direction constantly, rotating smoothly, completing one cycle at the same speed as each red, green, and blue phase omega, either in radians per second or cycles per second. The speed of the rotating field is known as synchronous speed and is designated in S, and can be in cycles per second, also known as revolutions per second, or it can be in radians per second, or it can be in revolutions per minute. It doesn't matter which designation you use, because they all can be converted to one another by a single factor, such as pi radians equals 180 degrees. It can be converted from cycles per second to radians per second. When comparing synchronous speed to the rotor speed, since rotor speed is usually in revolutions per minute or RPM, so should the designation of the synchronous speed. However, when comparing the synchronous speed of the frequency to the frequency of the supply, we're talking about cycles per second or radians per second. So you have to be aware and consistent when choosing and working with the designation. As I said, the speed in revolutions per second at which the rotating magnetic field revolves is called the synchronous speed, ns. I am demonstrating this in both the time domain at the top of the slide and graphically at the bottom right. You'll have to keep an eye on both as we move through one cycle. The time instant 4 represents the completion of 1/4 of that cycle of any of the 3 phases of the alternating supply currents from the time instant 1. But it is most obvious if we're looking at the red phase, so we'll just continue to look at that. During this 1/4 cycle, the rotation field has rotated through 90 degrees. If we were to carry on in equal increments, by time increment number 16, we would have gone through one complete cycle of the supply from the origin. The rotating field would have completed one revolution. Therefore, a 3-phase machine having 2 poles per phase in the stator winding, the rotating field makes one revolution in one cycle of the supply current. I have numbered each of the pole pairs 1 and 2 for each of the 3 phases. Let's take another look at the rotating magnetic field in this stator. As we have just seen, in a 2-pole per phase machine, the rotating field is in sync with the electrical supply. In order to differentiate between the supply and the rotating magnetic field, I'm going to refer to the supply oscillations as electrical, and I'm going to refer to the rotating magnetic field as mechanical. And it stands to reason because mechanical the mechanical rotation of the magnetic field will cause the rotor to rotate, and this is a mechanical action. So I have to differentiate between the two, so I'm going to call one electrical and the other mechanical. So for a 2-pole per phase machine, we have seen that the electrical angle velocity is the same as the magnetic or mechanical angular velocity. Keep in mind here the fact that angular velocity can be measured in more than one way. It can be measured in radians per second or in cycles per second, for example. However, when comparing the two, in other words, when we say the electrical angle velocity is equal to the mechanical angular velocity, we are talking about the angular velocity of both being measured in the same designations. We can also say that the electrical frequency is equal to the mechanical frequency, but here again, frequency sometimes is measured in revolutions per second or revolutions per minute. It doesn't matter which you use as long as we're consistent with both being the same. Now, what would happen if this pattern in the stator windings was repeated twice within the stator? This slide shows just such a stator. The pattern of the windings, taken from a counterclockwise direction, is X, Z primed, Y, X primed, Z, Y primed, X, Z primed, Y, X primed, Z, Y primed, which is just the pattern of the previous stator repeated twice for once around the circumference of the stator. When a 3-phase set of currents is applied to this stator, the oscillating field produced by the coils create a rotating magnetic field. The rotating field moves only halfway around the stator surface this time in one electrical cycle. That is to say, one electrical cycle goes through 360 electrical degrees, and the mechanical rotating field goes through 180 mechanical degrees. Clearly, the frequency of the supply is twice that of the rotating field. The relationship between the stator electrical angular velocity, omega E, and the mechanical angular velocity, omega m, is given by this equation. Or can rewrite the equation in terms of the electrical frequency or angular velocity in terms of the mechanical angular velocity. And that is for a 4-pole machine. What this means is that we can reduce the speed of a 3-phase induction motor by increasing the number of poles per phase. In this case, we have slowed the rotating field by 1/2 that of the 2-pole machine by increasing the number of poles to a 4-pole. machine. Therefore, we would be reducing the speed of the rotor. It is therefore evident that the speed of the rotor is inversely proportional to the number of poles per phase of the machine. Generally speaking, this is for a p-pole machine. The electrical angular velocity is equal to p over 2 times the mechanical angular velocity, or the mechanical angular velocity is equal to 2 all over p times the electrical angular velocity, where p is the number of poles per phase of the machine. If the angular velocity omega were in cycles per second, and if we were describing the synchronous frequency in RPM, or revolutions per minute, which is usually the case, then ns would equal 60 times omega. The result would now be in revolutions per minute. Sometimes the angular velocity omega is designated as frequency, and electrical frequency is the same as electrical angular velocity if measured in cycles per second. Then the electrical frequency would be equal to P all over 2 times NS all over 60, which would equal NS times P all over 120. Keep in mind that here electrical frequency is in hertz or cycles per second, and the magnetic field speed is in revolutions per minute. Sometimes we want to know what the synchronous speed is in terms of the supply frequency and the number of poles of the machine, and that is given by this equation. Let's go back to the two-pole stator because it's simpler to look at. If a three-phase supply is connected to the stator, it produces a rotating magnetic field in the air gap, which I've represented with a green phasor arrow. Its rotational speed is usually designated as ns RPM, and it could be CPS or radians per second, but it's more than likely going to be measured in revolutions per minute. The rotor rapidly accelerates in the direction of the rotating field. In practice, the rotor can never reach the speed of the stator flux. If it did, there would be no relative speed between the stator field and the rotor conductors, no induced rotor currents, and therefore no torque to drive the rotor. The friction and windage would immediately cause the rotor to slow down. As you can see, I've placed a red marker on the rotor so it can be easily tracked. I have slowed down the process quite a bit, so we were able to visualize what was happening. As you saw, the rotor was falling behind the rotating magnetic field. This is known as slip. The rotor speed is usually designated as N. Rotor slip speed is the difference between the synchronous speed ns and the rotating stator field and the actual rotor speed. Slip is expressed as ns minus n all over ns. And as you can see, it's more often than not a number less than 1. It can also be expressed as a percent, where the percent slip is equal to ns minus n all over ns times 100%. When the rotor is stationary, that is when n is equal to 0, the slip is equal to 1 or 100%. In an induction motor, the change in slip from no load to full load is hardly 0.1% to 3%, so that is essentially going to be called a constant speed motor. The phase sequence of the three-phase source applied to the stator winding is X, Y, Z in this case, and the direction of rotation of the magnetic field, as you see, was in a clockwise direction. If the sequence is changed to, say, XZY, it is observed that the direction of the rotation of the field is now reversed. That is, the field rotates counterclockwise rather than clockwise. However, the number of poles and the speed at which the magnetic field rotates remains unchanged. Thus, it is necessary only to change the phase sequence in order to change the direction of rotation of the magnetic field. For a three-phase supply, this can be done by interchanging any two of the three lines. As we shall see, the rotor in the three-phase induction motor runs in the same direction as the rotating magnetic field. Therefore, the direction of rotation of the three-phase induction motor can be reversed by interchanging any two of the three motor supply lines. This shows the equivalent circuit of a three-phase induction motor at any slip S. The rotor is assumed to be of a wound type and star connected. Note the rotor EMF per phase and the rotor reactance per phase are SE2 and SX2 respectively. The rotor resistance per phase is R2 and is independent of the frequency and therefore does not depend upon slip. Likewise, stator windings values R1 and X1 are not dependent on slip either. Since the motor represents a balanced three-phase load, we can use a per-phase analysis to study it, making it much easier because now we're just looking at a single-phase circuit. So we only need to consider one phase. The condition in the other two phases would be similar, but just out of phase by 120 degrees plus or minus. At standstill, the rotor current per phase is I2 is equal to E2 all over Z2. And since Z2 is the square root of R2 squared plus X2 squared, then I2 is given by the equation E2 all over the square root of R2 squared plus X2 squared. The rotor power factor is cosine phi 2 is equal to R2 all over Z2 and is equal to this equation. When running at any slip S, the rotor current can be given by this or these equations. The rotor power factor then is cosine phi 2 all over R2 all over Z2, which is equal to R2 all over the square root of R2 squared plus the quantity S times X2 squared. Let's have a look now at the rotor torque. The torque tau developed by the rotor is directly proportional to the rotor current I2, the rotor EMF E2, and the power factor of the rotor circuit cos phi 2, where I2 is the rotor current and E2 is the rotor EMF, and cos phi 2 is the rotor power factor. Or we can say that tau is equal to K E2 I2 cos phi 2, where K is simply defined as some constant. Since I2 at standstill is equal to this equation, and cos phi 2 at standstill is equal to this equation, which means we can now plug these two fractions in our previous equation to give us this big long one, what ultimately leads to this equation, k times E2 squared all over R2 all over R2 squared plus X2 squared. Since the starting torque is given by k times E2 squared times R2 all over R2 plus X2 squared, each of them squared in the denominator, and E2 varies as the supply voltage, the stator voltage, then the starting torque will vary with the square of the supply voltage. Therefore, the starting torque is very sensitive to changes in the value of the supply voltage. For example, a drop of 10% in supply voltage will decrease the starting torque by about 20%. This could mean the motor failing to start if it cannot produce a torque greater than the load torque plus the frictional torque. The rotor circuit of an induction motor has low resistance and high inductance. At starting, the rotor frequency is equal to the stator frequency, so the rotor reactance is large compared with the rotor resistance. Therefore, rotor current lags the rotor EMF by a large angle. The power factor is low and consequently the starting torque is small. When resistance is added to the rotor circuit, the rotor power factor is improved, which results in improved starting torque. This, of course, increases the rotor impedance and therefore decreases the value of the rotor current, but the effect of improved power factor predominates and the starting torque is increased. With squirrel cage motors, since the rotor bars are permanently short-circuited, it is not possible to add any external resistance to the rotor circuit at starting. Consequently, the stalling torque of such motors is low. Squirrel cage motors have starting torques of 1.5 to 2 times the full load value, with starting current of 5 to 9 times the full load current. In wound rotor motors, the resistance of the rotor circuit can be increased through the addition of external resistance. By inserting the proper value of external resistance, maximum starting torque can be obtained. As the motor accelerates, the external resistance is gradually cut out until the rotor circuit is short-circuited on itself for running conditions. When we apply mechanical load to the shaft of a motor, it will begin to slow down, and the rotating flux will cut the rotor conductors at a higher and higher rate. The induced voltage and resulting current in the rotor conductors will increase progressively, producing greater and greater torque. The motor and mechanical load will soon reach a state of equilibrium, when the motor torque is exactly equal to the load torque. When this state is reached, the speed will cease to drop anymore and the motor will run at a new speed at a constant rate. The drop in speed of the induction motor on increased load is very small. It is because the rotor impedance is low and a small decrease in speed produces a large rotor current. The increased rotor current produces a higher torque to meet the increased load on the motor. This is why induction motors are considered to be constant speed machines. However, because they never actually turn at synchronous speed, they are sometimes called asynchronous machines. Note that change in the load on an induction motor is met through the adjustment of slip. When the load on a motor increases, the slip increases slightly. That is, motor speed decreases slightly. This results in greater relative speed between the rotor flux and the rotor conductors. Consequently, rotor current is increased, producing a higher torque to meet the increased load. The reverse happens should the load on the motor decrease. With increasing load, the increased load currents, I2, are in such a direction so as to decrease the stator flux. This is according to Lenz's law, thereby decreasing the counter EMF in the stator windings. The decreased counter EMF allows the motor stator current I1 to increase, thereby increasing the power input to the motor. It may be noted that action of the induction motor in adjusting its stator or primary current with changes of the current in the rotor or secondary is very much similar to the changing currents occurring in a transformer that has perhaps a changing load. An induction motor may be considered to be a transformer with the rotating short-circuited secondary, or an electric load equated to the mechanical load of the motor. The stator winding corresponds to the transformer primary, and the rotor winding to the transformer secondary. However, the following differences between the two are worth noting. Unlike a transformer, the magnetic circuit of a three-phase induction motor has an air gap. Therefore, the magnetizing current in the three-phase induction motor is much larger than that of the transformer. For example, in an induction motor, it may be as high as 30 to 50% of the rated current, whereas it is only 1 to 5% of the rated current in a transformer. In an induction motor, there is an air gap, and the stator and rotor windings are distributed along the periphery of the air gap rather than concentrated on the core as in a transformer. Therefore, the leakage reactance of stator and rotor windings are quite large compared to that of a transformer. In an induction motor, the inputs to the stator and rotor are electrical, but the outputs from the rotor is mechanical. However, in a transformer, the input as well as the output is electrical. The main difference between the induction motor and the transformer lies in the fact that the rotor voltage and its frequency are both proportional to the slip, S. If the frequency F is the stator frequency and A2 is the per phase rotor EMF at standstill and X2 is the standstill rotor reactance per phase, then at any slip S, these values are rotor EMF per phase is S times E2. Rotor reactance per phase is S times X2, and rotor frequency is equal to S times F. Whereas in a transformer, the secondary EMF per phase is dependent on the transformer turns ratio. The transformer's secondary reactance per phase is fixed, doesn't change, and the transformer primary and secondary frequencies are always the same. From the slip equation, we can rewrite it to give the speed N of the induction motor in terms of slip, supply frequency, and number of poles per phase. Clearly, we can see that the speed of the rotation can be varied by changing the supply frequency, the number of poles P on the stator, and the slip. The speed of a squirrel cage motor can be changed by changing the number of poles. Only 2 or 4 speeds are possible by this method. For simplicity and learning purposes, we used a 2-pole induction motor. Since this motor would produce 3,000 RPM, it's not too practical in the real world. For this reason, only 4-pole machines given synchronous speeds of 1500 or 8-pole machines giving synchronous speeds of 750 RPMs are generally used. For this slide presentation, I have slowed down the process considerably. The rotational speeds you see here are only representative of the actual speeds. 4-speed motors are sometimes equipped with 2 separate stator windings, each of which provide 2 speeds. The disadvantages of this method are that it is not possible to attain gradual or continuous speed control. Speed control is in steps. And because of the complications in the design and switching of the interconnections of the stator windings, this method can provide a maximum of 4 different synchronous speeds for one motor. For wound rotor motors, their speed is changed by changing the motor slip. This can be achieved by varying the stator line voltage, by varying the resistance of the rotor circuit, and or inserting a varying foreign voltage in the rotor circuit. And this ends the chapter.